thanks very much. And yeah, thanks for coming back to the fourth lecture about Igusa stacks. So my last talk, I discussed compact Shimura varieties, and I said that in the kind of this talk, I will go to the non-compact case. And this is about joint work in progress with Linus Hamann and Yang-Zhu and Yang. So I didn't want to kind of take up too much time. I'm just using the same notation. So Gx is a Shimura datum, and this is my group over Qp. Hodge co-character mu, some number field, that's a reflex field. Then I choose a prime of that number field above a rational prime p, and I look at the corresponding p-adic field. And I'm going to have lambda as my coefficient ring. And I guess sort of for the beginning, it can be characteristic 0, so like QL bar or some finite extension of QL. And then later on, I'll just consider the L torsion case again. But the key point is, so I have residue characteristic, some other prime L different from P. OK, and so, right, as I said, I want to look at non-compact Shimura varieties. And so these admit various kinds of compactifications already, say, over the reflex field. And the kind of the compactification that I'm interested in is the minimal or Bailey-Borel compactification. And I hope I'll motivate why I'm considering this one. But so this is a compactification to a projective variety, but that is not in general smooth. And I'm going to denote by J the open immersion. So I'm looking at this non-compact case where this thing is projective but not smooth. All right, and then I want to kind of consider some kind of cohomology on this compactification. And the cohomology that I want to look at is the so-called intersection cohomology. And so I'm going to denote this by like the cohomology groups by IH of the Shimura variety. And with some coefficients in lambda, I'm going to define this as basically the hypercohomology of, well, cohomology of the following complex. So I look at the minimal compactification base change to an algebraic closure of E bar, and then I look at the middle extension of my sheaf lambda, which I shift by d and twist by d over 2, where d is the dimension. It's the same. Yeah, so this is open and dense in here, and the dimension is d. All right, and so one reason why I want to consider this is, well, it has better properties in this non-compact case than other kinds of cohomologies you could take. So for one thing, so this is a perverse sheaf that is just the constant sheaf lambda with this shift and twist on this open thing. But then there's kind of a unique way to extend it that's characterized in some sense. This is the middle extension, and this whose cohomology gives you something Verdier self-dual. So I should say maybe if you don't know what intersection cohomology is, kind of the slogan would be that it's something that kind of behaves like the cohomology of a smooth projective variety, but even works for things that are projective but not smooth. So this complex is Verdier self-dual, and it has lots of structures. So it has the same kind of Hecke action away from P that we've seen before. It has an action of the absolute Galois group of E, but it also has a Hodge structure and a Lefschetz structure. And I'm particularly interested in the Lefschetz structure. This tells you, so this will give you an isomorphism between IH in degree d minus k and IH in degree d plus k, where this is Hecke equivariant, but if I want to make it also Galois equivariant, then I take a Tate twist by k, and then k is some integer between, well, 0 and d. So in this sense, yeah, you have this really nice structure on the intersection cohomology of Shimura varieties. And the reason I want to look at it is to kind of try to understand, or, well, okay, so I should say that this part is really just, I forgot to do this, is motivation. So I want to try and put in some broader framework this kind of generic vanishing result that I discussed in my first talk, so the second talk in the course. And I'll say that at least when you work with characteristic 0 coefficients, there are conjectures of Arthur that describe this. I'll make this more precise in a second, but sort of roughly what they predict. So for now, this is just a rough statement. Predict that basically systems of Hecke eigenvalues that occur in degree d minus k or d plus k, and if they do, then because of the Lefschetz structure, they occur in kind of every other degree going from d minus k to d plus k, so you kind of jump by 2. Those systems of Hecke eigenvalues in there are more and more degenerate. So systems of HP eigenvalues occurring in IH, say d minus k, are more and more degenerate as k increases. Right, so kind of the one way to think about it is sort of if you really saw like somehow the associated Galois representation in cohomology, and you had some eigenvalue alpha in here, this would tell you that you should also see the eigenvalue, say, p times alpha, or whatever like residue characteristic you have, times alpha for some Frobenius. And so it's exactly kind of, you could imagine seeing, well, okay, here p to the k, and then all the way in between, you would have like a sequence, alpha, p squared alpha, and so on, up to p to the k alpha. So it's kind of sequences that exactly violate this genericity condition that requires you that you don't have any two eigenvalues with ratio p or p inverse. But this can, in fact, be made precise even if you don't see, like, you know, even if the Galois representation that you see in the cohomology of the Shimura variety is more complicated than kind of the one that is just associated by the Langlands correspondence. So like even if the R mu does something highly non-trivial to it. And to say something a bit more precise, I'm going to set, my Shimura variety, I'm going to view it as a locally symmetric space. So it's some smooth quasi-projective variety over this number field, but I embed it into C, and then this can be identified with a double quotient, where here I actually have the Hermitian symmetric domain that's part of the Shimura datum, and then cross G of AF, quotiented out by some k, by the same k over there, and then here quotiented out by G of Q. And this can be identified with the symmetric space, roughly the symmetric space for the real group, G of R, quotiented out by a maximal compact subgroup, and then possibly also quotiented out by some split torus over R where you need to take that quotient to get something of finite volume. So I'll just say this is like a symmetric space. Okay, and so if you also choose an isomorphism between QL bar and the complex numbers that I'm going to call iota, then you get the following sequence of isomorphisms that respect some of these structures that we're trying to understand on intersection cohomology. So I can take the IH upper star with QL bar coefficients via iota. This becomes isomorphic to intersection cohomology with complex coefficients. And over here, I still have the Heck action away from P, and I still have a Hodge structure and a Lefschetz structure. Okay, and now there's some kind of analytification of this. That's the thing that was studied first. This can be identified with the L2 cohomology of the locally symmetric space. So let me just write this for a second. So this is defined as the hypercohomology of the complex of square integrable smooth differential forms on this locally symmetric space, which is equipped with a Hermitian metric. Right, so square integrable smooth differential forms.
But the differential of a square integrable is square integrable, or you have to modify it so that you only consider things with differential is also square integrable?
Yeah. Yes, things where the differential is also square integrable. And so this is known as Zucker's conjecture. I apologize if I don't say it right. And this was proved independently by Luyanga and Sapir-Stern. All right, and the reason that I brought up this L2 cohomology is that this is further computed by work of Borel and Kesselman in terms of automorphic representations. Sorry. Right. So Borel and Kesselman compute this and show that it's a direct sum, so it decomposes quite nicely as a direct sum over only automorphic representations that are in the discrete spectrum. So pi, a discrete automorphic representation of G of the Adels, which I write as tensor product of some finite part and some infinite part. And then what you see is some automorphic multiplicity times the finite part, where I take k invariant vectors, and then this infinite part I take for it to be a Harish-Chandra module, and I look at the relative GK infinity cohomology of this Harish-Chandra module. And sort of, okay, for the talk, maybe it won't matter so much what these things are, so I don't want to spend too much time on it, but I'll just say that somehow the various structures that you see on intersection cohomology are sort of more separated here. So the Heck action is just on this side, on the finite part of the automorphic representation, And over here, you see the Hodge and the Lefschetz structures. And then, really, the automorphic multiplicity somehow ties everything together, because that's the kind of the multiplicity with which pi occurs in the discrete automorphic spectrum of G of the Adels. And so in particular, if you had something that wasn't automorphic, that would vanish, and then otherwise, well, right? So this is kind of the one that puts together the finite part and the infinite part. Okay, but then somehow, sort of one can compute this and see what range of degrees this part occurs in. So what range of degrees, in what range of degrees it is non-zero. And it turns out that this range of degrees is related to something called, well, it's related to the size of something called the Arthur SL2 of pi infinity. So kind of this range of degrees. And that kind of measures how degenerate your automorphic representation is. All right, so my motivation section is almost over. So I'll just say, and I encourage people to take a look at that, that Koshikawa and Shin wrote a recent paper, maybe finished at the end of last year, where they kind of take all the results that are known about vanishing of cohomology of Shimura varieties or more general locally symmetric spaces with characteristic zero coefficients and sometimes with torsion coefficients, and they try to understand it from the perspective of this general framework. And what they do is they formulate a conjecture about the range of degrees in which you can expect to see non-trivial cohomology that is given in terms of a representation theoretic condition at P. So Koshikawa and Shin formulate precise conjectures about the range of degrees where IH upper star is supported in terms of representation theoretic conditions at P. So that kind of has to do with thinking about kind of there's a global Arthur SL2 that will specialize to give you the Arthur SL2 of pi infinity, but also the one at P. But the problem is that Arthur packets are not disjoint, so there could possibly be different Arthur SL2s that one could see. So the representation at P could possibly be in different A packets, and then they appeal to something called the closure ordering conjecture to give some range of degrees in terms of some L parameter attached to something called the Aubert-Zelevinsky dual of the representation.
I'm sorry,
anyway,
sorry,
yeah.
Anna, I'm sorry.
Yeah.
I'm just lost because where is P?
P is over here. Okay, fine. So here I have some Hecke algebra, which I shouldn't have taken away from P. Sorry, I'm used to going to some infinite level at P, and then I only take some tame. But I mean, when you have an automorphic representation, you also have, factor at P that contributes in here. Okay. So, right, for now, I'm just kind of doing a very general thing where I've just chosen L, and P could be any of the rational primes.
Okay, so I think I understand this.
Sorry about this. That was my bad.
There's no motivation for the level at P?
Well, this is not really about, okay, sure, like you have this thing, right, that could easily vanish if pi p didn't have fixed vectors under whatever the level at P is. But that's kind of a trivial restriction. But the claim is as soon as you have some non-trivial invariant vectors here, suddenly you see the spreading out of degrees coming from this computation at infinity. And I guess one can ask if, so the question that so let me try and get, so there are some conjectures. These are for intersection cohomology. They specifically formulate them in characteristic 0. But then they work out some of the representation theoretic conditions also for in the torsion case. So you can extrapolate this question to the torsion case, where the range of degrees that you predict is somehow, you consider all the possible lifts to characteristic 0 and kind of the maximum range that these different possible lifts to characteristic 0 would give you. And right, they formulate some precise conjectures for torsion based on this idea for cohomology with compact support and for usual cohomology. And by putting those together, one could also expect something like that for intersection cohomology. Right, so that's one thing. I also wanted to mention that maybe Matt Emerton has kind of talked for as long as I've known him about how, oh, one should formulate a torsion version of Arthur's conjectures that exactly have to do with this kind of understanding the range of cohomological degrees. So let me also write Emerton here. And I want to say that, okay, basically these torsion vanishing results that I talked about on Tuesday fit precisely within this framework because this generic condition, it always guarantees that the Arthur SL2 always just has to be trivial. And that forces you to see those systems of Hecke eigenvalues only in the middle degree. Right? So kind of the generic torsion vanishing fits within this picture. And then there are some limited results that you can see even beyond the generic case. And the first such result shows up in work of Boyer in the Harris-Taylor case. And it's exactly this kind of this nature where you would look at a system of Hecke eigenvalues at P or the corresponding Frobenius eigenvalues, and you'd look at like the maximal chain like alpha, P squared alpha, and so on. And that maximal chain should predict the range of degrees where that system of Hecke eigenvalues can contribute. So, right, and then also in joint work with Matteo Tamiozzo, we proved something like this also in the Hilbert case, where kind of the defect is as just like 1 prime above P. Kind of can either be generic or fail to be generic, and then you count the number of primes that fail to be generic. And this is when P splits completely. Okay, so there's some kind of limited evidence that there might be something that happens beyond the generic case with torsion coefficients. Of course, if you put torsion coefficients, you no longer have access to this top row. Right? So with characteristic 0 coefficients, what you can do is exactly this. So some representation theoretic condition at P tells you something about the Arthur SL2 there. You go through the global Arthur SL2 to the Arthur SL2 at infinity, and you look at this computation here. But with torsion coefficients, this is not something that you can do. And then a question that is a motivating question, but I won't actually say much about in this talk, is, well, is there kind of a geometric mechanism that explains this kind of shearing of cohomological degrees? So a mechanism coming from the categorical local Langlands program, for example, in the setting of Fargue and Schulze. Okay, and I'll say that, again, there is something very suggestive in the work of, so this is work in progress of Bertoloni-Milli and Koshikawa. Let me see. They construct some, but purely in the setting of local Langlands. They construct some generalized eigensheaves for local Arthur parameters that have this kind of shearing property. So usually an eigensheaf, you would apply a Hecke operator and you'd expect to see the same eigensheaf tensor with that Langlands parameter. That would be in the setting of trivial Arthur SL2. But more generally for Arthur parameters, what you see is you see the parameter but kind of sheared out and occurring in several cohomological degrees. And that seems to match the kind of structure that you see here. But it's not clear how to see the work of, how to see the purely local eigensheaves constructed by Bertoloni-Milli and Koshikawa in the setting of Shimura varieties. Okay, so this is the motivation for the talk, is we want to construct a sheaf on Bungie that recovers intersection cohomology of Shimura varieties. And that then can be studied by applying Hecke operators to it, or generally with methods from categorical local Langlands program. So this is part 2, is the main theorem. And so roughly the goal, before I state the main theorem, it'll take me a bit. So roughly the goal is to construct some sheaf that I'm going to call FIC in D Bungie lambda that kind of computes intersection cohomology in the same way as we saw in the talk on Tuesday. Right? So kind of put intersection cohomology also in this more geometric framework, where you can ask how it compares to purely local objects. All right, so now I'm going to go to a very special Shimura datum. So I didn't have you choose one, but now I'll say that under certain technical assumptions. So the problem is we need a minimal compactification of the Igusa stack. But under certain technical assumptions, we have this. Right, so the Cartesian diagram that Mingjia wrote and proved, in certain cases, you can extend it to the minimal compactification and see the minimally compactified Shimura variety in the top row. And so these are technical conditions, but I don't think they should be considered like, I don't know. Yeah, they should really be considered technical and removable in the near future. That's my expectation. So GX is of PL type AC. And G, so the group over QP is unramified. And then also, so pick your favorite Shimura variety, possibly the modular curve, except that I want to assume that the codimension of the minimal compactification minus the open part, so the codimension of the boundary should be at least 2. So you can still do the modular curve, but only with a grain of salt. But this is really just technical. Okay, and then you have a Cartesian diagram constructed by Mingjia in her PhD thesis. So now I move to slightly different notation, because I work in this, over this p-adic field and with diamonds. So the Shimura variety at infinite level, but now minimally compactified, living over the flag variety, which lives over Bunji, and there is a minimally compactified Igusa stack here. And I'm going to, for simplicity of notation, I'm going to call pi bar Hodge-Tate this map that really sees the minimal compactification. Okay, and this is the Hodge-Tate period morphism. This is the Beauville-Laszlo map. Remember, this was L cohomologically smooth, so nice in the setting of p-adic geometry, have smooth phase change available. Okay, and within this, you have the usual diagram for the Igusa stack. This sits in here as an open immersion, but something that I want to emphasize here is that there's two different kind of Igusa stacks that you could consider. You could try and have just, say, the open Shimura variety at the top, by which I mean the complement of the Zariski closed boundary, or you could have the good reduction locus. And something that is important for what I want to do next is I want to really consider kind of the complement of the Zariski closed boundary, right? So you should think of the difference between closed unit disk and an affine bowl, right? So the bigger one is the affine bowl. That's the analog of what I want to consider here. Okay, and so this part here is due to Kim, right? So, and it uses, you'll see in the talk tomorrow, that it uses this kind of unique characterization of Igusa stacks to construct this. All right, and now, so maybe just to put as a warning here, that this is really not the same thing as the good reduction locus. So the good reduction locus, there's also a Cartesian diagram for that. That's the one constructed by Mingjia, but it's harder to compute with that sometimes. All right, and now if you think about how you might want to solve the problem of defining a sheaf here, right, that will give you intersection cohomology, or that will compare nicely to some purely local eigensheaves. Well, there's two things you can try to begin with. So there's some obvious sheaves, but unfortunately, they're both just semi-perverse. Yeah. So I can write F lower shriek, which is the push forward, let me say here, less than or equal to mu inverse, so that this map becomes surjective, and in particular, so that this map is proper. And so just doesn't matter which push forward I take, but I look at J lower shriek of lambda. So I take the constant sheaf on the complement of the boundary and take the extension by 0. This is in perverse degree less than or equal to 0. So in one half, right? It's kind of just in one of the two full subcategories that define the T structure, but not in the other. And the way that you prove this is by showing that this has stalks given by cohomology of Igusa varieties, but there's again some kind of extension by 0, where the usual Igusa variety that has this nice moduli theoretic problem of trivializing the p-divisible group over the special fiber of the Shimura variety, so really lives over a Newton stratum or even over an Oort central leaf. This thing admits a partial compactification that is an affine scheme over FP bar. So this thing here is affine. And so these are really usual schemes. And for this reason, you can use Artin-vanishing to show that this is in degrees from 0 to the dimension of the Igusa variety. And that exactly checks that this sheaf is, I guess, upper semi-perverse, I think. Okay, and then by Verdier duality, you can consider another sheaf that is lower semi-perverse, F lower star, that would be I'll take Rj lower star of lambda, right? That's another thing that you can try. And then just from Verdier duality, this is because pi Hodge Tate bar is proper, this is in perverse degree greater than or equal to 0. Okay, and those stalks can be computed in a more subtle way. So it's not as immediate as this computation, but they end up just being the usual cohomology of the open Igusa variety. Okay, so I'll just say here, and this is more subtle. Okay.
Are there no shifts because I saw the dimensions work out in some nice way?
Oh, I'm sure there are shifts. Yeah, I'm sorry. I should have put shifts.
I'm sorry.
Yeah, maybe I should have done this so that I really get degree 0, maybe.
That looks promising.
That looks promising. Okay, let's leave it at that. Yeah, sorry about this. Right, so imagine that maybe there are shifts and twists. Okay. So
can you say a bit about how do you get the stalks can be computed?
yeah, so I guess you have to essentially prove some intermediate result. So it's true for if I took the good reduction locus, it would be true. And so you have to compare the push forward from the complement of the boundary with the push forward from the good reduction locus. And essentially you can, in my second paper with Scholze that deals with a non-compact case, we have a bunch of arguments that essentially prove this, even though it's not written in that language. So it kind of goes to infinite level at L and makes use of Pink's formula on the Shimura variety side and on Igusa varieties. Okay, so I think I can finally finish with the motivation. So these are only semi-perverse. And I'll say that the people working in categorical local Langlands expect that eigensheaves are perverse, maybe even the generalized eigensheaves. But for eigensheaves being perverse, for example, you can look in Hansen's Beijing notes, and there's a heuristic there that has to do with, kind of stalks are computed in terms of coherent Springer sheaves, and there's a conjecture on what degrees of cohomology the coherent Springer sheaf lives in, and kind of how the perverse structure on Banji matches the perverse T structure matches some other T structure on the side of Langlands parameters. So these being semi-perverse, they're not good enough to just directly compare with eigensheaves. So that's one thing. Another thing is if you try and compute these stalks using like a counting point formula, you'll see that this doesn't directly compare with the geometric side of the trace formula. And somehow you have a nicer computation if you were able to take like the intersection cohomology, like the middle extension with respect to this open immersion seems to give you something nicer from this kind of trace formula perspective. And so yeah, somehow you need a perverse sheaf and something that maybe is computable nicely, and maybe that connects to intersection cohomology, and so that's essentially what we do in this work in progress. So I'll just say that it's better to have a perverse sheaf. And okay, you could say, well, why don't you take kind of the truncation, perverse truncation of one, of the other, take the image, and that might work, but it's not clear how that compares to intersection cohomology. But essentially, yeah. We expect that the sheaf that we construct is exactly this kind of perverse truncation of F lower shriek, and take the image of that in the perverse truncation of F lower star. All right, so the theorem that is joint work with Hamann and Zhang says, sorry, and now I have to remember what the, So let me, for simplicity, state this in the torsion setting. There exists a sheaf FIC in D Bun-G lambda, which is ULA, and I said this is a technical condition that shows up in the work of Fargues and Schulze, and that's very close to requiring a sheaf to be reflexive from the point of view of Verdier duality, and that kind of makes Verdier duality interact better with the 6 functors. And once you know it's ULA, you can prove that it's Verdier self-dual, and then you can prove that it's perverse just by doing 1/2, so the being in perverse degree less than or equal to 0, plus the perverse T structure here is stable under Verdier duality, gives you this, and then which satisfies that if I apply T mu to this sheaf, and then I pull back to the neutral point, so along this open immersion I1, I view this as a smooth representation of GQP with lambda coefficients, and this turns out to be the same as the colimit of these, well, let me write it p-adically. Of the middle extension at each finite level, which is some fixed tame level and then some level at p that goes to 0. Okay, and this is kind of in D smooth GQP lambda, and also Hecke equivariant now for the Hecke algebra away from P, because I have the full representation of GQP at P, and also equivariant for the Weil group action. So let me say WE equivariant. Okay. And I actually want to say something about ideas involved in the proof, but before I get to that.
So what is I1?
This open immersion. I1 takes the neutral point of Bun-G into the whole of Bun-G, and then remember this is just the classifying stack of GQP, and so the category of sheaves here is identified with this category of smooth representations of GQP.
Sorry, what is this J lower shriek lower star lambda?
So for each of these, you have an open immersion of the Shimura variety into its minimal compactification. And I guess I could index the J by the level if you wanted. And then it's a middle extension, right? So it's the general definition of the middle extension pulled back from the algebraic setting.
So you'd have to check the bottom thing is saying it's like the intersection homology, but you find infinite bottom.
Yeah.
Okay, cool.
Except that, no, I mean, well, okay, so it's a bit subtle because it's not true that if you pull back the intersection complex at one finite level, you get the intersection complex at another finite level. So what you have to take is, at infinite level, the cohomology of the minimal compactification with coefficients in the co-limit of the pullbacks of all the intersection complexes. But there are still maps between them, so you can still define Hecke correspondences, but of course, like, yeah, there's some subtlety with how the intersection complex varies as you vary the levels. Sorry, does anyone see where my eraser went for the board? Am I completely just missing it, or? Okay, there's something here, never mind, I found something.
Oh, I think it's
Thank you, thank you.
While you're erasing, Anna, do you know if there's a map from F lower shriek to FIC or from FIC to F lower star?
So we expect, yeah, I mean, we expect to be, it's work in progress. We expect to prove that it's exactly the thing I described.
And at the moment, you don't know maps? Or, well,
I think there must be maps. I'm just almost certain that we can prove the thing. It's just we haven't written it, so that's why I want to, yeah. Okay, so corollary. This will be quick. So torsion vanishing in the generic case for intersection cohomology, but unfortunately under the assumption that L is banal for GQP. Right, so concentration in the middle degree, but when you try to descend to finite level, you don't have Hochschilds there for intersection cohomology in general, and that is a snag. And then Eichler-Shimura relations, which were proved in this setting by Wu, except maybe we can do something slightly stronger by going to Iwahori level instead of just hyperspecial level. So again, for intersection cohomology. Okay, and these are proved in exactly the same way as I explained on Tuesday. Right, so you have all the formalism, but now with this sheaf, FIC. So I don't have to go through the proof. And I can just spend some time kind of with some ideas in the proof of the theorem. Right.
This sheaf, is it pushed forward from some sheaf?
Yeah, it is. I wanted to state some simpler. I didn't want to spend forever stating the main theorem, and so I just went to the push forward on Bungie. But it is constructed by looking on the Igusa stack and defining an intersection complex there, and then taking the push forward. So, okay, so ideas in the proof of the theorem. So, okay, so yeah, I mean, the first thing is you want to define some kind of intersection complex. IC on the minimally compactified Igusa stack. Okay, and define FIC as R pi Hodge Tate bar lower star of IC Ig star. Yeah.
I have a question. So then, would you expect like then a decomposition theorem of this, and it's going to break up into the sum of generalized eigensheet? Like, is that
we do not know how to show that it breaks up as a direct sum.
Is that like a philosophy that like the kind of decomposition into like generalized eigensheets would now be like a decomposition theorem in this context?
Yeah, if you had a decomposition theorem, you'd be in good shape. Yeah, I don't know. For now, I should say that one thing that my collaborators and I, and also with Bertoloni, Melli, and Koshikawa, is we're just trying to even just formulate a precise conjecture in the spirit of this conjecture of Arthur. So with the multiplicity formula in terms of these generalized eigensheaves. But yes, it's true that one should prove.
But that's the idea. That's the sort of philosophy.
Yeah.
That's awesome.
Well, okay, but I'm not claiming that I know how to do that. Okay, so this is what we want to do. And the other thing that we should be careful of is that there's no general theory of perverse sheaves in p-adic geometry. And so that's why, essentially, we want to define an ad hoc T-structure on Ig star. And what we show is that Ig star has a stratification into boundary strata, and the boundary strata are L cohomologically smooth of a particular dimension. And then we kind of give some specific T-structures on the strata, and then we glue. So that's the idea. To write it more precisely, I need board space. So that's kind of the first step, is really a geometric step, which is to define a boundary stratification in the setting of the Igusa stack. All right. Okay, so And so the Shimura variety at the top, even GQP equivariantly, admits such a stratification. So on the Stacky level, you have something like this, a disjoint union over some index where I call the elements P of S sub, well, okay, fine, still some infinite level, tame level, and P, and again divided by this. All right, where P runs over equivalence classes of admissible rational parabolic subgroups of G. Okay, and essentially you can descend under this L cohomologically smooth map from the Shimura variety side to the Igusa stack side. You can descend at least the strata on the level of, say, the topological space, or even on the level of the V stack. So we construct a stratification. But okay, let me put this in quotation marks. I mean, we construct it ultimately. So maybe that's okay. Disjoint union over the same classes of parabolics of strata, okay? But somehow, so you can kind of take the image, but then what you want to do is take the image under the map from the Shimura variety to the Igusa stack, but then you can ask, well, do these images intersect? Or like if I pull back, if I take the inverse image of the image, do I get back the same thing? And so we prove a Cartesian diagram for boundary strata. Where, so at the top, I have this thing. This goes to the flag variety. This goes to Bangji. And here I have the stratum in the Igusa stack also labeled by P. And remember, so this was L cohomologically smooth, even of dimension D. And then, so proving that this is a Cartesian diagram, actually, like, you reduce to checking what happens with points, but essentially what you want to do is, like, as you have different P's, you want to make sure that the kind of images don't collide. And you can essentially check it on the level of kind of partial compactifications of Igusa varieties more classically. So kind of involves studying the action of this group GB tilde on the fibers of the pi Hodge state bar, which are identified with these diamonds associated to more classical Igusa varieties. But then you also have toroidal compactifications that have more of a moduli theoretic flavor. And so you can define such an action moduli theoretically, essentially. Okay. And so then these strata are L cohomologically smooth of dimension D minus, D sub P, whatever it is, some dimension, minus D, where this is L cohomologically smooth of that dimension. Just give me a sec. Dimension dp. So this is, well, you can view it in two ways, right? You can view it as the automorphism of E, right? Of a G bundle on the Fargues-Fontaine curve, the one corresponding to the element B of the Kottwitz set. Or you can think of it as the diamond associated to automorphism of the universal cover of a p-divisible group over FP bar. This interpretation is better for studying the action on the Igusa variety.
So is this something obvious in the perfection of the Igusa variety?
It has the same dimension, but I mean, it's a group that shows up in the work of Fargues and Schulze, right? So each stratum here is the classifying stack of GB tilde. Okay. So, right. So this allows us to actually get a T structure that is even stable under Verdier duality. And so then we define our intersection complex ICX. And I have 5 minutes, so some ad hoc perverse T structure on D Ig star lambda. And so this allows us to define IC Ig star as the middle extension. And now this one is fine with the shift, like it is the right thing. Okay. And then we have to prove that this is already ULA with respect to a point. And once you know it's ULA, it's not too hard to show that it's Verdier self-dual by kind of copying the kind of proof, the kind of classical proof that this middle extension, right? There's a characterizing property for it, and you verify it for it, and it's Verdier dual. Okay, the ULA-ness, this is by comparison with the algebraic. So when you pull it back along the L cohomologically smooth map to the Shimura variety, you can compare it to the algebraic IC sheaves at finite level. So roughly you pull back to the Shimura variety at infinite level and then take invariance, and this compares to the algebraic IC sheaves at finite level, which are, I guess, the risky constructible on this rigid space with a minimal compactification. Okay, and then you want to prove perversity and Artin-vanishing. So prove perversity from Verdier self-duality and Artin-vanishing. And first I'll tell you why it should be true morally, and then I'll tell you what argument we need so that we can actually prove it. So morally what happens is that if you look inside some Igusa variety, this also has some stratification that's inherited from the stratification on the Igusa stack. And this has dimension, let's say, dp upper b or something. No, that's a d. Okay, upper b. And then there's a transversality result that tells you that somehow the Newton stratification and the boundary stratification are transverse to each other. So roughly it's that the codimension, so dpb minus db, the codimension of the stratum in the Igusa variety is constant as b varies over bg mu. And it's the same as dp minus d. And also that somehow the stalks of IC Ig star on boundary strata, like, on XP, or maybe pulled back to the Shimura variety, are locally constant. And this ultimately follows from Pink's formula, which tells you that the nearby cycles are locally constant. So morally, this is what you want to put together. Somehow you know, somehow, the cohomology sheaves, and if you look at, no, sorry, I meant cohomology sheaves here, not stalks. Okay, you look at that, and if it's supported on a stratum, that stratum has to have a certain codimension. And somehow it works out that you're able to prove that FIC lands in perverse degree less than or equal to 0. But the extra problem that I'm going to finish with is that you want to apply Artin-vanishing in this kind of setting of p-adic geometry. And it's not immediate how to reduce it to an algebraic setting. that's something that maybe we took for granted when we were doing compact Shimura varieties, or even, you know, when you take like the F lower Schriek version. So here, I'll just say, so this is okay for characteristic over a characteristic zero base, but for a kind of rigid space, and this is due, I think, independently to Hansen and Morrow. Sorry, Matthew, I'm sorry. I apologize. Yeah. Yes, that's particularly egregious. But we are over an aphanoid perfectoid base. The last name and first name collided in my head also. So that's one issue. And then we thought, oh, maybe we could tilt. But then if we tilt, the problem is that in characteristic P, it's really only known for certain sheaves that are somehow algebraic in some sense. For example, for the constant sheaf. Right, so once you tilt, you can find some limit to cases that are known, but only when you have the constant sheaf. This is due to Gaber and Zavyalov. And then we kind of just prove something that is adapted to our situation, and I don't know if it's ever going to be useful in any other situation. Essentially, we follow this argument of Hansen. That's an inductive argument. Stay in characteristic 0, but somehow reduce to the case of the constant sheaf over some base that we know is aphanoid perfectoid, and then we tilt to characteristic B, and we do some argument with limits to reduce to something known. And it's really useful to know that ultimately our sheaves come from these algebraic sheaves on the Shimura variety, even when you kind of look at their kind of intersection with an Igusa fiber that kind of sits in some weird way inside the perfectoid Shimura variety. And let me just end with something that we hope to prove, but we're not 100% sure yet. But something that we hope is that the stalks IB upper star of FIC are kind of this thing. So you can take the middle extension of the constant sheaf, maybe with some shift and twist, on a classical Igusa variety, and take the cohomology of that. And if that was the case, if we were able to prove this, that would give another way to see perversity via Artin-vanishing. And it also would be something that would be computable. All right, so I'll end here. Thanks.
Okay, thank you. Any questions?
Yeah. So related to Dustin's question, so with this definition, it looks like there's an obvious map from J to a Schriek and
yeah, sorry. The problem is I cannot think in my head, and so, but yeah. Yes, there is an obvious map, and essentially the way that we think we can prove that it's, you know, the truncation of the F lower Schriek and take the image of that and the truncation of F lower star is that this argument for Artin-vanishing is slightly more general than just applying to particularly this IC complex, right? It kind of uses these properties. This is about the dimension of the strata, and this is about the sheaves. So it's kind of has potential to be more flexible.
Thank you.
Let's come back of IC Igusa commodification. Go back to even level Shimura variety should be the one constructed like the white person's one. Right?
It's slightly subtle because, so I wrote this Shimura variety up there as a stack quotient. And so for instance, if I look at some, and I guess, okay, so like if I were to pull back to some like stack quotient mod KP, that is different from literally the coarse moduli quotient, that is the Shimura variety at level KP. So there's some subtlety from the fact that kind of the compact open subgroups in GQP kind of act freely on the open part away from the boundary, but then the action is ramified at the boundary. But we are able to prove a comparison of this pull back, but it's just slightly more subtle.
So at the beginning you mentioned that like kind of spreading out in several cohomological degree. Can you like find explanations like in terms of some geometric Langlands procedures from this?
So if you were to conjecture, right, that say if I localize at some system of Hecke eigenvalues away from P here, conjecturally this thing is like one of the generalized eigensheaves that Bertoloni, Melli, and Koshikawa construct, or some summoned in it, or something, then that would explain it. Of course, you could conjecture it. I expect it's a very hard conjecture to prove.
Okay, so if there's no more questions, let's resume at 3:20, which is probably 3:25 up there, and let's thank Anna again.